In the previous installment, we discussed what might have occurred within the first second after the Big Bang. Starting from the separation of gravity from a hypothetical superforce to the subsequent functioning of the four fundamental forces, the universe underwent a rapid expansion, transforming from a quark-gluon plasma to the confinement of quarks into particles like protons and neutrons. During this Hadron era, the basic components for forming atomic nuclei were prepared. So, what incredible events lay ahead for the universe? Today, let's continue exploring the post-Big Bang occurrences. As we mentioned earlier, after the Hadron era, the energy density of the universe was no longer sufficient to produce heavy baryons like protons and neutrons. Instead, lighter particles known as leptons were generated. These included electrons, muons, neutrinos, and their corresponding antiparticles. When positive and negative electrons, positrons, generated during this period annihilated, they emitted photons through pure radiation, converting the mass of the electrons into photon energy. This process, known as recombination, might be the moment referred to in the Bible as "let there be light." Interestingly, this annihilation process is reversible. Under sufficiently high temperatures, around 6 billion degrees Celsius or 10.8 billion degrees Fahrenheit, photons colliding can recreate electron-positron pairs. Around 10 seconds later, as the universe expanded further, the protons and neutrons formed during the Hadron era began to combine to create atomic nuclei. Initially, most of these nuclei were simple, like hydrogen nuclei composed of single protons. After about 1 to 2 minutes, some neutrons joined in, forming heavier nuclei like deuterium, heavy hydrogen. However, deuterium was unstable at this point and would be destroyed by high-energy photons, leading to a phenomenon termed the deuterium bottleneck. Around a minute later, as the universe continued to expand, the energy of photons decreased, allowing stable deuterium nuclei to form. This marked the onset of nucleosynthesis, during which heavier elements like tritium, helium, and trace amounts of lithium were produced. These light elements found in the universe today can be traced back to this nucleosynthesis period. Observations of element abundances in the universe align closely with the predictions of the Big Bang model, serving as compelling evidence for its validity. After nucleosynthesis concluded, the subsequent epoch was much longer. During this phase, about 75% of the universe consisted of hydrogen nuclei and 25% helium nuclei, along with some negatively charged electrons and numerous high-energy photons. With atomic nuclei and electrons now freely present, photons scattered frequently due to their interactions, making the universe opaque. However, gradually, as electrons combined with atomic nuclei through recombination, photons decoupled from these interactions, marking the decoupling era. In the decoupling era, photons could travel freely, causing the universe to become gradually transparent, akin to streets clearing after people return home in the evening. As these unobstructed photons traveled through the universe, their wavelengths stretched due to cosmic expansion, resulting in microwave radiation. This radiation, known as the cosmic microwave background, is the afterglow of the Big Bang. Its temperature has decreased from over 3,000 degrees Celsius, 5,432 degrees Fahrenheit, to just under 3 degrees above absolute zero. These photons are the earliest sources of light in the universe. During this phase, there were no other light sources apart from this cosmic microwave background radiation. Since these photons grew fainter due to cosmic expansion, this period is often referred to as the Dark Ages. It wasn't until around 240,000 years after the Big Bang that the universe cooled down enough for electrons to combine with atomic nuclei, forming neutral atoms. This event led to a transition from the opaque universe to a transparent one, allowing photons to traverse unimpeded. This era is known as the recombination era. Post-recombination, photons could travel freely, and they carried information about the universe's early state. Over time, these photons redshifted, with their wavelengths lengthening due to cosmic expansion. This redshifted light now appears as microwave radiation, and it constitutes the cosmic microwave background radiation. It's often referred to as the echo of the Big Bang, as it originates from the decoupled photons of the recombination era. This radiation has a temperature only slightly above absolute zero, around 3 degrees Kelvin. After the cosmic microwave background radiation, there was a period with no discernible light sources. However, after about 500 million years following the Big Bang, the first generation of stars began to form. These early stars emerged from small fluctuations in the matter distribution, potentially arising from quantum fluctuations in the vacuum. These fluctuations led to gravitational attractions that facilitated the aggregation of matter into denser regions, eventually birthing primordial stars. As these matter-rich regions continued to collapse under gravity, the core densities of these protostars grew, eventually reaching the threshold for nuclear fusion. This fusion ignited the stars, marking the birth of true stars. These first stars are referred to as the population 3 stars, or sometimes the metal-free stars. Comprising almost entirely of hydrogen and helium, they lacked heavier elements, which would only be produced through subsequent stellar fusion processes. However, these massive stars had short lifetimes of a few million years and are challenging to observe, making them elusive. Subsequently, after these early stars had formed and died out, the universe started producing heavier elements. These elements are often referred to as metals in astronomy, which doesn't imply actual metals but rather all elements except hydrogen and helium. With the presence of heavier elements, subsequent generations of stars formed as metal-poor stars, or the population 2 stars. As more and more stars formed, influenced by the gravitational framework of dark matter, they clustered together into the first galaxies. Although primitive, these galaxies were active, containing objects like quasars, extremely luminous and active galactic cores. These objects emitted high-energy ultraviolet radiation, causing reionization, a process where previously neutral matter became ionized again. The details of the reionization era are still being explored, but it is believed to have concluded roughly 1 billion years after the Big Bang. Following this, galaxies and galaxy clusters proliferated in the universe. There are 2 main theories regarding galaxy formation. The first, proposed in the 1960s, suggested that galaxies formed through the collapse of a massive gas cloud, followed by the gradual appearance of stars as the gas rotated within the galaxy. However, this top-down theory is no longer widely accepted. The prevailing theory is the bottom-up approach, which posits that galaxies originated from small clumps that gradually merged to form dwarf galaxies. Over time, these dwarf galaxies merged to create larger galaxies, possibly including our Milky Way. This theory aligns with the observed abundance of small galaxies in the universe. In summary, as more galaxies formed, the universe evolved into its recognizable state. This covers a brief overview of the history of the universe following the Big Bang. According to the Big Bang theory, our universe started with minimal components and fundamental physical constants, and it developed over time through natural processes to its present state. Even if a creator existed, they may have merely set the initial conditions. Today, everything in the universe has evolved naturally.